Last week, we learned how to manipulate bits in a computer. We have yes, we have no, 1, 0, and we know how to manipulate them. But what can we do only with 1 and 0? Can we represent more sophisticated things with them? Of course, we must if we want to use a computer to do useful things. But what can you do with only two values, 0 and 1? Well, you definitely can put two of them together, and then you get 4 possibilities. 3 of them together, you get 8 possibilities. In general, if you have n of them together, you have 2 to the n possibilities, and now you can represent any 2 to the n different things that you may want to. For example, you can represent numbers, and this is what we're going to be interested in. How are you going to represent integer numbers? Well, 0 is easy. 0, 1 is easy. Last week we learned how to is already the first problem, basically because we have yes, we have no, 1, 0, and we know how to manipulate them. But what don't have yet another possibility, so we have to use 2 bits. 0, 1, 0. 3 is 1, 1. For the next one, we already need another bit, 1, 0, 0, 4, 4. And in general, it seems we can represent any numbers that we want with some sequence of bits. Now, how did we connect the sequence of bits, the binary representation of an integer number, to the integer number? What's going on? What's the general system? In order to understand that, we have to go back to second grade, when we learned about decimal numbers. We see 789. What does that mean? What does the digit 7, 8, and 9 have to do with the value of the number 789? Well, we learned that we have the positional system, where the rightmost digit is the ones, the next one is the tens, the next one is the hundreds. So we know that 789 is really 9 plus 8 tens plus 7 100s, and so on. In general, the case position from the right is 10 to the k. So now exactly the same thing is going to happen also with binary numbers, but it's going to be much simpler because we only have 0 and 1 rather than all the digits between 0 and 9. Thus, in binary notation, the different positions will be powers of 2. 1, 2, 4, 8, and so on. Suppose you want to know, for example, what is the value of 101 in binary notation. Well, we know the rightmost bit is basically the 1s. The next one, the 0, corresponds to 2s, and the third, the leftmost bit here, is the 4s. Altogether, we have 4 plus 2 times 0 plus 1 times 1. Altogether, that's 5. So our number is 5. And in general, what do we do in general? Exactly the same thing. You have any sequence of bits, and we're going to number them from the rightmost bit, which is going to be b0, the next one b1, and so on, all the way to bn, if we have n plus 1 bits. And the value of this thing is going to be b0 times 2 to the 0, plus b1 times 2 to the 1, plus b2 times 2 to the 2, all the way until the nth bit, which we have, where we have bn times 2 to the n. And this is going to be a number. And that's how we can convert any sequence of bits, any binary representation of a number, to the value of a number. One thing that we should note at this point, that if we look at the maximum number we can represent with k bits, well, we sum up from 2 to the 0 all the way to 2 to the k minus 1. Remember, there's a kth bit. If we start counting from 0, the last bit is counted is indexed to k minus 1. So we have the sum of 1 plus 2 plus 4 all the way to 2 to the k minus 1. Altogether, we have 2 to the k, all that minus 1. And that's the range of bits we can actually represent with k, the range of numbers we can represent with k bits. Now, so far, we assumed we have an arbitrary length number of bits that we can use to represent. And of course, if we want to represent an arbitrary long number, we will need an arbitrary number of bits. In computers, you usually have a fixed number of bits that is allocated. And then, of course, you will only be able to represent a fixed range of the integer numbers. So, for example, if we only have 8 bits, what are the possible numbers you can represent? Well, you can represent something starting with 0, 0, 0 8 times, 0, 0, 0 and ending with a 1, all the way up to 8 ones. The smallest number is, we have altogether 256 such possibilities. The first one is index 0, the last one is index 255. Now, that's not exactly true. Really, when we have 8 bits, usually we want to reserve part of all the possibilities to actually represent negative numbers. We're not going to actually talk about this now, but rather in a unit from now. But in general, half of the 256 possibilities are going to be reserved for negative numbers, and we're only going to be able to use the numbers between 0 and 127, and these are the positive numbers that we're going to be able to use out of these 256 possibilities of 8 bits. To use numbers, half of the 256 are actually. Now, that's not exactly true. Really, when we have 8 bits, usually we want to reserve part of all the possibilities to actually represent negative numbers. We're not going to actually talk about this now, but rather in a unit from now. But in general, half of the 256 possibilities are going to be reserved for negative numbers, and we're only going to be able to use the numbers between 0 and 127, and these are the positive numbers that we're going to be able to use out of these 256 possibilities of 8 bits. So far, we saw basically if you get a string of bits, how can you convert it to decimal numbers? Now we're going to do the opposite thing. Suppose you're given a number in decimal, 87, for example. How can you represent it as a sequence of bits? This is also something that we should be able to do if we're going back and forth between decimal notation and binary numbers that are actually going to be represented in the computer. Well, remember that we know that really the way we get the decimal from the binary is by summing up powers of 2. So we started figuring out what is the largest power of 2 that fits into our 87 number, and that is going to be 64. And then what is the next one? After we have 64, what is the next power of 2 that we can add to 64 and we still remain under 87? That turns out to be 16. And so on, we can keep on going, and we write the number 87 as a sum of powers of 2. And it turns out that 87 is exactly 64 plus 16 plus 4 plus 2 plus 1. And once we have that from this representation of the decimal number as a sum of powers of 2, we can quite directly actually get the binary representation. How do you do it? Well, every time we have a power that appears in the sum, we need to put a 1 in the bit there. And whenever the power is not part of the sum, we put a 0 there. So for example, look at the rightmost bit. That corresponds to the 1s. We do have a 1, so that's going to be a 1. On the other hand, if you look at the third bit from the right, which is correspond to the 8s, since we don't have 8 in our sum here, we're going to have 0s there. And that's basically a general way how you can take any number and convert it to binary. So This concludes this unit where basically we discussed how you can represent integer numbers within a binary system. In the next unit, we're going to actually discuss how can we actually perform arithmetic operations, in particular addition, on these represented binary numbers. Once we get that under our belt, we will go back and discuss the issue of negative numbers in unit 3. In the last unit, we saw how to represent numbers in computers using binary bits, but now we can represent numbers. That's the important thing. Now, the whole point of representing something is if we want to manipulate it. What kind of manipulation do we want to do with numbers? Well, we want to add them, subtract them, multiply them, and so on. This is what we're going to learn how to do in this unit. Well, not all of them. What we will really be talking about is how to add. Once we do that, we'll basically get the whole rest, all the other operations almost for free. It turns out that once we understand how to represent negative numbers, which we will do in next unit, we'll be able to get subtraction for free and to understand which of two numbers is greater for free. Multiplication and divisions are more complicated, but nicely enough, we can actually postpone them to software. We will not build in hardware any multiplication or division circuitry, but rather we will actually let software do it, and things are much easier to do in software because you just have to write little programs rather than actually connect stupid little devices. So we get two sequences of binary numbers. How can we add them? Well, one way we already know how to do, and that's going to be very easy. We convert them to decimal. We add the decimal numbers that we know how to do from second grade. We get a decimal number, we convert it back to binary that we just learned how to do, and we get the answer. This is great and fine, but of course that's not what a computer does. A computer doesn't know how to add decimal numbers without first converting them to binary numbers. So we need to figure out how to actually do the addition of binary numbers and directly without converting them to decimal. And how are we going to do that? As usual, everything that I need to know I learned in second grade, so we need to go back to second grade. We need to add 5,783 plus another number. How do we do this kind of addition? What did we learn? Well, we start with the ones, with the rightmost digit, and we add 3 plus 6, we get a 9, and we're all very happy with that. That's easy. But now what happens when we do the next digit, and we have 8 plus 5? Well, if 8 plus 5 is 13, and we cannot write 13 underneath the tens position because 13 is greater than 10. So we all learned this important and amazing trick of writing only 3 and having 1 as a carry to the 100th place. And then we know how we can continue from there. And then we can add the 1 to the 7 and so on, and after we finish with the leftmost digit, we have the complete result. So exactly the same thing we're going to do in binary numbers, only it's going to be much, much easier. So we take 1 plus 0, the rightmost two digits, and we need to add. The first is more easily do the same kind, and now we can continue. We need to add 1 plus 0 plus 1. Now we have 1, 1, and that's how we continue until we get the final solution, the final answer, and that's all there is to it. In the rest of the unit, we'll actually learn how to do this thing exactly, how to do this thing completely mechanically, in the sense of really understanding how every operation works in terms of binary operations that we've learned so far. But the basic principle is extremely simple, just like we learned in second grade. Before we continue, there's one thing I want to take out of the way, and that is the question of overflow. Suppose that we were somehow unlucky, and the two leftmost bits of the two numbers that we were adding were 1. So what is the problem with that? The problem is that when we add them, we have a carry that needs to go to the left of the word size, and there's no place to put that carry bit because we finished our word size. So what do we do? Will we raise some warning or anything like that? Well, the answer is very simple. What is usually done in computer systems is nothing. We just ignore any carry bit that does not fit into the word. What does that mean, really? So if you try to look at it from a mathematical point of view, what it means is that the addition that we are actually doing in our hardware is not real integer addition, because we cannot go beyond the numbers that fit inside the word size. Instead, what we have is really addition modulo 2 to the width of the word size, if you look at it mathematically. In other words, the answer is correct, but except for the case that it may be off by exactly 2 to the n, where n is the word size. If the result was more than 2 to the n, the hardware automatically decreases 2 to the n, which is basically the carry that we just threw because there was an overflow. So that's what we usually do, and the rest of anyone using a computer, anyone using computer and software, needs to remember that if he exceeds the word size, then the result that you get is not the true integer result of the integer addition, but rather the truncated result after the overflow was already disposed of. Once we got that out of the way, let's go back and try to understand how are we actually going to build this kind of an adder. How can we actually build hardware that gets two numbers as bits, as input bits, and the output is another number that actually represents the sum of the two input numbers? We'll do that in 3 easy stages. In the first stage, we'll just learn how to add 2 bits. Very simple. The second stage, we'll learn how to add 3 bits. It may seem there's a long way to go if we are progressing so slowly, but then in one big step we'll be able to add any two numbers of any number of digits. So let's start with that. So let's look at the typical operation when we were adding two bits in the process we just looked at. How do we took a 1 plus 1 and we added it and we got a 0 sum and a 1 carry? How did we do that? Well, the most important thing is to notice that the rest of the bits of all these two numbers do not matter at all when we're doing just this one bit slice of operation. Whatever the other bits were, as long as what we're adding now is 1 plus 1, and as long as one additional important thing, the carry so far, the carry we had to this place was 0, whatever the other bits are, we still are doing the operation exactly the same. We're going to put right 0 below these two ones, and we're going to have a carry of 1. The thing, the carry so far do not matter at all when we're doing just this one bit slice of operation. How do we took a 1 plus 1 and we added it and we got a 0 sum and a 1 carry? How did we do that? Well, the most important thing is to notice that the rest of the bits of all these two numbers do not matter at all when we're doing just this one bit slice of operation. Whatever the other bits were, as long as what we're adding now is 1 plus 1, and as long as one additional important thing, the carry so far, the carry we had to this place was 0, whatever the other bits are, we still are doing the operation exactly the same. We're going to put right 0 below these two ones, and we're going to have a carry of 1. This tells us that now we have really just a simple binary operation, taking two bits, A and B, and producing two output bits which depend only on them, which is one of them we're going to call the sum, the binary sum of these two things, and the other is the carry. And this is really the first step that we need to do. This will actually allow us to add two bits. Now this operation really, which is a slice one step of the process that we saw so far, is that's naturally abstracted by a chip. And the chip gets two inputs, A and B, two outputs, and we know exactly for every combination of inputs what the output is supposed to be. This chip is called a half adder, and implementing it is the first thing that you'll do in the exercise for this week. In fact, we're going to give you the exact HDL that describes the interface of this chip, and you're just going to have to do the implementation, which actually does implement this operation that we now understand what it is. And we're finished the first step of our journey to add numbers, adding two bits. Now, if you remember, the only real restrictions that we had when we were doing this addition of two bits was the fact that the carry to this point was 0. But that's not the general case. What happens more generally if there may be a carry? Suppose now that we get another bit as the input called C, which describes the carry from the previous step, which can be either 0 or 1. Now, how do we do this addition? Well, we know we add the three numbers and we still get a sum and a carry. Again, now we get a Boolean gate, a chip if you wish, that we know exactly its functionality. We have three inputs, A, B, and C, two outputs, sum and carry, and there are 8 possibilities of the inputs. And for each of them, we can very well know what the outputs are. So that's another chip. And that chip is called the full adder. And again, you can just go and implement it. And indeed, this is the second part of our journey to addition. And again, we're giving you the HDL of this chip, and please go ahead and implement it. And now we're ready for the final step for doing everything. We get two full numbers, and we want to add them. How are we going to do that? Well, we already know how to do every single step of the process, so we just have to repeat doing this single step. So let's look at what we did. Let's color the bits, the rightmost bit yellow, the next one green, the next one blue. This is just so we can talk about them in terms of colors, but of course in the implementation there are no colors, just different bits. So we start, of course, by adding the two yellow bits, and adding the two yellow bits is just a half adder because we have no carry so far, and we get a yellow sum and a yellow carry. Now the next step is we need to add the yellow carry to the two green bits, and from that we get a green sum and a green carry. Now we take the green carry, add it to the two blue bits. Each one of these colored steps is simply a full adder now. The thing that takes the yellow carry, the two green bits, and outputs a green carry and a green sum, that's just a full adder. And that already we've implemented. So to implement the whole thing, we just need to basically connect 16 of these full adders, or maybe 15 full adders and one half adder for the rightmost bit, connect them together in the right way, and you get exactly an adder. And this is what you're supposed to do. This is our 16-bit adder. It accepts two numbers now. Each one of them is a bus of 16 bits, and outputs a single number that is supposed to be their sum as 16-bit integers. And again, we're going to give you the HDL for this. It just specifies that you're going to get two 16-bit numbers as buses in input, and produce a single number, 16-bit bus is output, that is their sum in terms of 2's representation of the number. And you can go ahead and implement that. So we just learned how to add two numbers in a very concrete sense of building the chips that actually do that. The next unit will actually go back and actually look at how to represent negative numbers, something that we still owe you from last unit. Once we do that, it will turn out that we'll get subtraction for free. After we get that under our belt, representation of the number. And you can go ahead and implement that. So we just learned how to add two numbers in a very concrete sense of building the chips that actually do that. Sum, that's just a full adder, and that already we've implemented. So to implement the whole thing, we just need to basically connect 16 of these full adders, or maybe 15 full adders and one half adder for the rightmost bit, connect them together in the right way, and you get exactly an adder. And this is what you're supposed to do. This is our 16-bit adder. It accepts two numbers now. Each one of them is a bus of 16 bits, and outputs a single number that is supposed to be their sum as 16-bit integers. And again, we're going to give you the HDL for this. It just specifies that you're going to get two 16-bit numbers as buses in input, and produce a single number, 16-bit bus as output that is their sum in terms of 2's representation of the number. And you can go ahead and implement that. So we've just learned how to add two numbers in a very concrete sense of building the chips that actually do that. The next unit will actually go back and actually look at how to represent negative numbers, something that we still owe you from last unit. Once we do that, it will turn out that we'll get subtraction for free. After we get that under our belt, then we'll go to the capstone of this week's lecture, which is building a complete arithmetic logic unit. And it turns out that most of the cleverness is already done. The most clever thing we have in an ALU unit is just adding two numbers. But of course, we need a lot of logic around it, and that's what we'll do in the fourth unit. In the last two units, we've seen how to represent integers as binary numbers using bits, and how to manipulate them, how to add them. But so far, we only discussed positive numbers, and of course our computers will have to deal also with negative numbers. So how can we deal with them? So let's take for example the case of 4 bits. So we know there are 16 possible values there, and what we've done so far, we represented the integers between 0 and 15, all 16 numbers of them, using the 4 bits. In general, so far, if we had n bits, we use them to represent the positive integers between 0 and 2 to the n minus 1. If we want to represent negative numbers, we will need to give up part of these 16 possibilities in order to represent negative numbers. So maybe 8 of them will be positive and 8 of them will be negative, or something like that. So how can we do that? Well, the simplest thing you may consider, and it was used sometimes, was to basically take the first bit and use it as a sign bit, and then you have 3 more bits, or n minus 1 more bits in general, to represent the actual number. So this way, if it starts with 0, it's going to be just a positive number. If the first bit is 1, then the next 3 bits, and it's going to be a negative number that is represented by the next 3 bits. In this case, we can represent 0, 1, 2, all the way up to 7, and then negative 0, negative 1, all the way up to negative 7. So this will be one possibility of representing negative numbers, possibility that is not very popular. Why? There are a bunch of problems with it. One thing that you may immediately notice, this is very inelegant. We have negative 0. What is this negative 0, and why is it different than 0? What we learned in math was that 0 equals negative 0. So of course, we may in principle decide to have 2 representations of 0 in our computer, but that is inelegant and probably means there's going to be trouble. Usually, if you have something that's not elegant, it's going to bite you. And in fact, here, if you actually try to manipulate these kind of negative numbers using some kind of hardware, you'll get into trouble. You'll need to explicitly deal with pluses and minuses, and the whole thing will be a mess. So hardly anyone uses this anymore. Here is what people use instead. They use a system called 2's complement, and it has a very simple idea. If you want to represent a negative number, negative x, you just instead represent a positive number 2 to the n minus x. In our case of 4 bits, 16 minus x, which is going to be a positive number, and you're going to represent it like we've seen so far. So for example, in our case, here are the numbers. You have 0, 1, 2, all the way up to 7 as usual. Now, if you want to represent, let's say, negative 3, well, you present negative 3 by the integer 16 minus 3, which is 13. So if you look at the place 1, 1, 0, 1, which is really the binary number 13, the value of that is negative 3. So this is basically the table that we have so far, and this system is called 2's complement representation. So let's look what we get in this representation. First of all, the positive number numbers that we have are half of what we previously had. Basically, we're missing a bit, so we can represent all not the numbers up to 2 to the n minus 1, but rather up to 2 to the n minus 1, all that minus 1. The negative numbers in this system, we get one more of them, so we get all the negative numbers between negative 1 and negative 2 to the n minus 1. And in our case, we get the negative numbers between negative 1 and negative 8, but we get only the positive numbers between 1 and 7, and of course we have the 0 as usual. So the main thing that's nice about this trick is that we will basically get our addition and subtraction and almost all the operations that we need to do with numbers almost for free. So let's see what does that mean. Suppose that we want to add 2 to the n minus 1, and in our case, we get the negative numbers between negative 1 and negative 8, but we get only the positive numbers between 1 and 7, and of course we have the 0 as usual. So the main thing that's nice about this trick is that we will basically get our addition and subtraction and almost all the operations that we need to do with numbers almost for free. So let's see what does that mean. Numbers almost for free. So let's see what does that mean. Suppose that we want to add 2 numbers. What I'm going to show now, that if we just use the same addition circuitry that we built so far, we'll magically get the correct result. And this is true not only in this example, but in general. So let's look what happens if we just take negative 2 plus negative 3 using our circuitry that was not designed for negative numbers, but just designed for positive numbers as we've done in the last unit. So here's what happens. So negative 2 plus negative 3 is, if we use 2's complement, that's really 14 plus 13. So 14 plus 13, we know how to add in binary. We get the 2 binary numbers. So 14 plus, we use 2's complements. So for positive, look what happens. Result. Just use the sum and subtraction and almost all the operations. operation that we need to do with numbers basically get our usual. Now, -1 missing complement representation. So let's look what we get for 14, 13. Well, you present -3 case plus you just have said and the whole thing will be a mess. So hardly anyone uses this anymore. Here is what people use. So hardly anyone uses this anymore. Here is what people use to present a number, which is so for usual negative case 1 supplement representation. So let's look our how not that. So we get all the negative 2 to z. Basically, we're missing a bit, so we can represent all not the numbers up to 2 to the n minus 1, but rather up to 2 to the n minus 1, all z minus 1. The negative numbers in this system, we get one more of them, so we get all the negative numbers between -1 and -2 to the n minus 1. And in our case, we get the negative numbers between -1 and -8, but we get only the positive numbers between 1 and 7, and of course we have the 0 as usual. So the main thing that's nice about this trick is that we will basically get our addition and subtraction and almost all the operations that we need to do with numbers almost for free. So let's see what does that mean. Suppose that we want to add two numbers. What I'm going to show now, that if we just use the same addition circuitry that we built so far, we'll magically get the correct result. And this is true not only in this example, but in general. So let's look what happens if we just take -2 plus -3 using our circuitry that was not designed for negative numbers, but just designed for positive numbers as we've done in the last unit. So here's what happens. So -2 plus -3 is, if we use 2's complement, that's really 14 plus 13. So 14 plus 13, we know how to add in binary. We get the two binary numbers, and just we add them using the previous circuitry. So here's the sum if we just use the previous thing. Here's the usual sum of these two numbers. Now notice that there was a carry bit, the one that is in green there, that usually in our circuit we threw away. So what does that mean? So really the output that we get is 1 0 1 1, and the most significant one was thrown away. So what does that mean? Well, the original result without throwing the carry bit is really the number 27, which is what it should be, the sum of 14 and 13. Once we threw that away, we lost 16 because the next bit that was thrown away is equal 16. So what we get is only 11. Now what's nice about 11? So basically what our hardware computed was that 14 plus 13 equals 11. What is nice about 11? Well, 11 in 2's complement really represents the number -5. And this is exactly what we needed to do. So amazingly, we got the correct result without doing anything new. Now, how does that happen? Why does this magic happen? Will it always happen? Well, as we saw in the last unit, our addition is anyway modulo 2 to the n. That is, because we throw the overflow bits, the result that we get is correct up to an additive 2 to the n, the additive factor. And our representation is also modulo 2 to the n, in the sense that we represent two numbers as equal, -3 and 13, are equal up to an addition of exactly the same 2 to the n. And since both our representation and addition have the same convention, then they exactly fit, and we don't need to do anything else, but immediately our hardware that was designed as previously just for positive numbers just works like it is. So one thing we may still need to do is, given a number, get its negation. So given as input x and a binary number, to output its the number negative x, again in 2's complement. Why would we want to do that? Well, for one thing, remember that we still didn't see any circuit that does subtraction. But once we can solve this problem, then definitely we have already solved the subtraction problem. Because if you want to do y minus x, you just need to add negative x to y. And addition we already know how to do. So once we can compute negative x from an input x, we've already solved the subtraction problem, and that's a good thing because we don't have to build new hardware for it. So the basic idea of how to do this kind of negation in 2's complement is very simple. It uses a mathematical trick that 2 to the n is actually 2 to the n minus 1 plus plus 1, and thus we can rewrite negative x, which is really 2 to the n minus x in 2's complement as 1 plus 2 to the n minus 1 minus x. That may seem completely crazy. What have we gained so far? But here's one very nice thing about this. 2 to the n minus 1, if you look at that as an integer number, that is a binary number, that's represented as bits, as all 1 bits. So it's just 1, 1, 1, 1, 1, n bits of 1. What's so nice about that? It's very easy to subtract a number from this because you never need to borrow anything. So in order to represent 1, 1, 1, 1, 1 in binary minus any x, you just need to flip each one of the bits. It's very simple. You never need to borrow from the next one. So this is a very simple Boolean operation, just negation. Once you've done that, now we only need to add 1. And this is very nice because we already know how to add in general, so of course we know how to add 1. So now we've seen that using this very simple trick, basically we can now do subtraction, again, just by the fact that we know how to do addition. So let's see an example. Let's see how we can design a Boolean hard circuitry that takes as input x and produces as output negative x in 2's complement. For example, takes 4 as input and produces negative 4. So again, what would negative 4 be in 2's complement? It would be the bits 1, 1, 0, 0, which represent 12, which is 16 minus 4, is the way we're going to represent negative 4 in 2's complement. 12 in 2's complement, it would be the bits 1, 1, 0, 0, which represent 12, which is 16 minus 4, is the way we're going to represent negative 4 in 2's complement. So how are we going to do that? Well, our input is 0, 1, 0, 0. That's 4. Remember, the first thing that we did, we needed to do 2 to the n minus 1, the all 1's bit, and subtract our number from it. So this is the first thing we do. We take the all 1 and subtract the number from it, and then we just flip the bits and we get the result. Now we need to add 1. So we just add 1 to it, and we know how to add 1, and we got the new number, exactly what we needed to get, the number 12, that is the number negative 4. Now, in general, we need not worry too much how to add 1 to a given number because we know how to add any numbers, but this is a special case, so it may be worthwhile to actually note what happens. How do we add the same 1 to a number? Well, if you look what happens if you just do addition, well, you start adding 1. If the list rightmost bit is 0, you just turn the 0 to 1 and you got your new number. If it's 1, you turn the 1 to a 0 because you add 1 plus 1, and then you have a carry, and you move to the next bit from the right. And again, if it's 0, you turn it to 1. If it's 1, you turn it to 0, but you need to keep on going because you have another carry. So in general, basically, what you do for the special case of adding 1 to a given number, you start from the rightmost bit, you keep on flipping bits until you reach a 0 that you flip to 1, and at that point you stop. And that is a very simple hardware to manipulate. You don't to actually build. You don't need to write a completely general addition circuitry, although you may. And we got our result. So we finished now to say how we deal with negative numbers, and the most important point is that we don't need to do anything new really. We just need to understand what we're doing, and everything that works for positive numbers will keep on working as long as we're careful enough about that. And now we're ready to actually design the arithmetic logic unit of a computer, and we will not really need to do any special thing, neither to subtract numbers nor to handle negative numbers. They will all be taken care of themselves once we understood this way to represent negative numbers. In this unit, we're going to talk about a very important component of every general-purpose computer called the ALU, or the Arithmetic Logic Unit. Back in 1945, the great mathematician John von Neumann wrote a seminal paper in which he included a diagram or a description of how general-purpose computers can be built. And this became to be known over the years as the von Neumann architecture. Now, when you look at this diagram, you see that one key player in the diagram is the central processing unit, and within this CPU, yet another important piece is the ALU, or the Arithmetic Logic Unit. Now, if we abstract away all these details and focus only on the ALU, we can think of an abstraction which receives two multi-bit inputs. We call them input 1 and input 2. And the third input is the function that has to be computed. So the ALU computes the function, and out comes the result of this computation. Now, the function f is one out of a family of predetermined functions that, taken together, define what this ALU is capable of doing. Some of these functions are arithmetic, and some of these functions are logical. So, for example, common computations that ALUs typically perform are integer addition, integer multiplication, integer division. There may be some logical operations like bitwise AND, bitwise OR, and so on. So there's a really interesting question, which is when you set out to build an ALU, how much functionality do you want to build in this hardware device? Well, this is the classical hardware-software trade-off question, because if you choose not to implement something in hardware, you can always augment it later with software. So if for some reason you decide that the ALU will not include multiplication or division, presumably at a later point when you build your software layer, you will complete this functionality with software. All right, now, so far, everything that we said was true for every ALU out there on any computer. From now on, we're going to focus on one specific example of an ALU. We call it the heck ALU because this is the ALU that will hum in the inside our heck computer. This is the overall gate diagram, and as we see, the ALU has two 16-bit data inputs, which we call x and y. It outputs a single 16-bit output, which we call out. Which function to compute is determined by 6 control bits that have strange names like zx and nx and so on. We will explain these names in just a few minutes. And based on these 6 control bits, the ALU computes one out of the following 18 functions of interest. And I call these functions functions of interest because, in principle, the ALU can compute many more functions, but we decided to focus on these 18 functions only. Now, some of these functions are very simple, like the constants 0, 1, -1, x, y, and so on. And other functions are more involved and interesting, like x plus y, x and y, and so on. Now, as we see from the diagram, the ALU also computes two 1-bit control outputs, which are called ZR and NG. The role of these two control bits and the reason for these names will become clear later in the unit. All right, so let's move on and focus on the output of the ALU from one side and the control bits that cause the ALU to compute these outputs. And they cause it using this truth table. So this truth table gives you a complete functional specification of this ALU. That is, if you want to compute a certain function, you can look it up on the right-hand side of the table. You can then read off the zeros and ones that correspond to this function. You enter these zeros and ones into the control bits, and boom, using some sort of black magic, the ALU will compute the desired function. So let me illustrate how the ALU works in action, and in order to do it, I'm going to use our hardware simulator. So we can fire up the simulator, we can load the built-in ALU chip, and as a result, we'll get this chip into the HDL window. And once we do that, notice that we also get some nice GUI. And indeed, some of the built-in chips in our simulator have a GUI side effect that helps the user, you, to understand what goes on inside the respective chip. So this is a diagram that we made up to help you keep track of what happens inside the ALU. So moving along, we begin testing. As you can notice, we have set the ALU inputs to two values, which are 30 and 20. And we also set the control bits to 0, 0, 0, 1, 1, 1, which, if you look at the table that I showed you before, what they mean is it's a directive that tells the ALU compute y minus x. So the next thing that we do is we have to tell the simulator to actually do something, and we do it by clicking this calculator icon, and this tells the ALU to evaluate the chip logic on the given inputs. So this is what happens next, and then we can inspect the outputs, and if we do that, indeed we see that the ALU came out with what was advertised, which is minus 10, the result of y minus x. So it looks like the ALU, at least in this example, works well. All right, let me give you a second example which demonstrates the logical computational capability. It's a directive that tells the ALU compute y minus x. So the next thing that we do is we have to tell the simulator to actually do something, and we do it by clicking this calculator icon, and this tells the ALU to evaluate the chip logic on the given inputs. So this is what happens next, and then we can inspect the outputs, and if we do that, indeed we see that the ALU came out with what was advertised, which is minus 10, the result of y minus x. So it looks like the ALU, at least in this example, works well. All right, let me give you a second example which demonstrates the logical computational capabilities of the ALU. The first thing that I do is I tell the simulator to revert to working with Boolean formats rather than decimal formats, which make it much easier to enter zeros and ones into the various inputs of the ALU. And that's what we do here. So I picked up two arbitrary examples of 16-bit zeros and ones values. I entered them, and then I entered also the control bit values 0, 0, 0, 0, 0, 0, which happens to be the directive to compute x and y. Once again, if you look at the truth table, you will see this row listed out. And indeed, after we click the calculator icon, which I skipped in this example, we see that the ALU actually computed a bitwise AND operation, and the result is the bitwise AND of the two given inputs. So far, it seems like the ALU is functioning quite well, at least in these two examples. All right, well, we didn't say anything about how the ALU actually works. Everything so far was kind of magic, so now is the time to open up the black box and understand how the ALU actually performs this magic. every one of these bits. So of what x is, it can be 17 or 19 or 5003 or whatever, we set it to 0. That's what we do if zx is 1. If nx is 1, we set the x input to not x. This is bitwise negation. And also notice that these two things happen one after the other. So for example, if zx equals 1 and nx equals 1, first of all, we zero the x input and then we negate it. So we'll get 1, 1, 1, 1, 1, 1, if this is indeed the values of these two control bits. The same thing exactly happens. And also notice that these two things happen one after the other. So for example, if zx equals 1 and nx equals 1, first of all, we zero the x input and then we negate it. So we'll get 1, 1, 1, 1, 1, 1, if this is indeed the values of these two control bits. The same thing exactly happens. Notice the values of these two control bits. The same thing exactly happens. Notice that these two things happen one after the other. So for example, if zx equals 1 and nx equals 1, first of all, we zero the x input and then we negate it. So we'll get 1, 1, 1, 1, 1, 1, if this is indeed the values of these two control bits. The same thing exactly happens with the y input using the zy and ny directives, if you will. Then we have an f bit. If f is 1, we compute x plus y. If f is 0, we compute x and y. Now, these are the processed x and y. So before we do these computations, the x and y's have already undergone these manipulations that we talked about before. They became either 0 or negated or nothing, maybe we didn't touch them, and then we compute either addition or 16-bit ending. Finally, we have the NO bit. If the NO bit is 1, we negate the resulting output, the output that we just computed, and if NO is 0, we leave it as is. If we do all these operations one after the other, then what comes out is the desired function. And now that you understand this semantics, you can actually look at the table and try to convince yourself. You can actually prove that this table delivers the required results. And I will demonstrate to you how we can do it. So let's pick up one example. Let's see how the ALU computes not x. So I look up not x in the right-hand side. I see it right there. And then I look up the binary values of the 6 control bits, and I start simulating on paper what happens inside the ALU. So in order to do it, I have to come up with some arbitrary examples of x and y. So I make up 2 values, and I use 4 bits instead of 16 to make it less tedious. So I have these 2 examples, x and y arbitrarily chosen. And then I look at the control bits. Zx equals 0 and nx equals 0, which means that we don't touch the x input. We leave it as is. Chosen 2 and 7. This is arithmetic operation, so it's easier to think about it in both in decimal and in binary. So we have 2 and 7, and if everything works well, we should get the result 5, because y minus x, 7 minus 2, should give us 5. So we see that zx is 0 and nx is 0, so we don't touch the x input, it remains as is. And moving along, we see that zy is 0, so we don't touch the y input, but ny is 1, which means that we have to negate it. So 0, 1, 1, 1 became 1, 0, 0, 0. Moving along, we see that f equals 1, so we compute the addition, and if we add up x and y, we get 1, 0, 1, 0. NO also equals 1, so we negate the result, and we get 0, 1, 0, 1. And 1, 0, 1 represents 5, which is exactly what we wanted. So once again, you see that the ALU performed. We see that f equals 1, so we compute the addition, and if we add up x and y, we get 1, 0, 1, 0, and nx is 0, so we don't touch the x input, it remains as is. And moving along, we see that zy is 0, so we don't touch the y input, but ny is 1, which means that we have to negate it. So 0, 1, 1, 1 became 1, 0, 0, 0. Moving along, we see that f equals 1, so we compute the addition, and if we add up x and y, we get 1, 0, 1, 0. NO also equals 1. So we negate the result, and we get 0, 1, 0, 1. And 1, 0, 1 represents 5, which is exactly what we wanted. So once again, you see that the ALU performed as specified. And many of you may still wonder how this magic actually happens. We were told that we have to do subtraction, and actually we did addition, and we got the result that we expected. Well, we don't want to get too much into it, but if you go back and read or look at the units where we discussed the two